Hi everyone. I guess let's start with like a quick show of hands. Who here is like familiar with Bitcoin and like the intricacies? Okay, not so. I heard you're more like cryptographers and not like blockchain. Who is like more on the cryptography side than on the blockchain side? If this is two things like cryptography, huh? And who would rather identify as like a blockchain person? Okay, okay. So I'm going to talk about BitVM. You probably know zero knowledge proofs. Have you heard of zero knowledge proofs? Who has heard of zero knowledge proofs? They are the hot topic, of course. Yeah, and BitVM is essentially a way to hack zero knowledge proofs into Bitcoin to build bridges and to bridge Bitcoin to second layers. And in particular, I'm going to talk about the third iteration of BitVM, which is called BitVM 3, and garbled circuits. Who has heard of garbled circuits? Cryptographers usually like garbled circuits. We might be the first people in the world who have actually a use case for garbled circuits. Like a quick overview, what is BitVM about? Well, BitVM is about building bridges. And we want to bridge Bitcoin to second layers. That means like to rollups and to side chains. In general, it's a scalability solution. And we are doing that by doing optimistic snark verification. Ideally, we would do snark verification just like in Ethereum. However, the scripting language of Bitcoin is very basic, very primitive. And that's why we actually cannot verify a snark directly on Bitcoin, so we have to verify it optimistically. And we have these roles called operators. They operate the bridge, they process the withdrawals. And if they do some funny business, then you can slash them. You can prove that they have been lying, that they have acted maliciously. And BitVM is essentially a mechanism to slash them if they act maliciously. And the security assumptions, if we have one honest operator, if we have one live operator, then the bridge is live. That means people will eventually get their money. And even if all the operators are malicious, they cannot steal from the bridge. However, that is only true as long as we have one honest challenger who challenges the malicious operator in case something happens. So one live operator is required for liveness, and one honest challenger is required for safety. And that improves over the state of the art. Previously, we just had multi-sigs, which is kind of like the trivial way to do bridges, and now we can reduce it to a one-of-n assumption. And quick overview about the state of BitVM 2. Well, we have founded this so-called BitVM Alliance, and this is 9 companies that are working on it, and we have implemented it. The implementation was already completed in March 25, and you can use it here, like you can check it out here. It's all open source, MIT licensed. And we just completed our security audit, and hopefully within the next month, the first BitVM 2-based L2s are going to launch on Bitcoin. And to give you a rough idea how that works, Bitcoin is completely stateless. Ethereum is very stateful. You have that state tree, and you can easily store state in that state tree. Bitcoin is kind of like the opposite. It's designed to be completely stateless. So we need to pile all kinds of like tricks on top of each other to hack state into Bitcoin. And one of these tricks is so-called connector outputs. And it works such here. So, like this. Okay, we have some kind of parent transaction. So this is like the abstract mechanism, and in the next slide I will show you exactly how we built the bridge with it. But this is the abstract mechanism that is important to understand how BitVM bridges work. We have some kind of parent transaction, and in Bitcoin we have outputs. We don't have accounts, we have outputs, and essentially every output represents a coin. And here in that parent transaction, Alice creates a coin, and she pre-signs this coin to spend it with the conditional transaction. And in Bitcoin there's a thing called SIG hash all, which allows you to not just sign your input, but also sign a sibling input. So you are merging both of these inputs into a single transaction. And usually you are doing that because, I don't know, you have a coin that is you want to pay 10 and you have a coin that is 7 and a coin that is 3, so you have to merge them to pay 10. Here we are actually abusing this mechanism to introduce state. Alice has 10 and we are paying 10, but we are adding another output, and this is only to introduce state. Because this way we make this conditional transaction depend on the condition transaction. And in Bitcoin it's possible to compute the ID of this output before that transaction was executed. I can just look at this input and then compute this transaction off-chain before I execute it, and then I know this transaction ID, which identifies this output, and then I can compute essentially the signature for this and express that the conditional transaction can be executed exactly if the condition transaction was executed before. And this allows us to implement essentially a conditional, because if there's any alternative transaction that spends this output, then the conditional transaction is rendered obsolete and you cannot spend it. And this expresses essentially, you can execute the conditional transaction exactly if the condition transaction was executed and the connector was not spent in any other way. This is the abstract mechanism behind our bridges, and now in the next slide I'm going to show you how we actually use that in a bridge. Well, Alice packs in, let's say, 100 BTC into the bridge, and she sends it to an N of N multisig. This is essentially like a so-called covenant emulation, but it's not really important. This covenant, or like this committee, they pre-sign the peg-out transaction, and this peg-out transaction depends on 2 outputs. And these 2 outputs come from the so-called kickoff transaction. And this kickoff transaction is executed by the operator in the moment where they want to process a withdrawal. When somebody wants to take money out of the bridge, and they have initiated that withdrawal in the sidechain or in the side system, then afterwards the operator says, okay, now I'm going to take money out of the bridge. And once they execute the kickoff transaction, they create these 2 outputs, and one of them is time locked. This is this one, and this ensures essentially the challenging period. It forces the operator to wait for 2 weeks until they can execute the peg-out transaction. And the second one is that connector output where we essentially encode the logic in. And this connector output, the operator pre-signs a slashing transaction during setup, and here the BitVM is essentially a black box. But if the watchtower or the challenger, if they win the game, the BitVM game against the operator, essentially if they disprove the operator, then the watchtower, they win an output that allows them to execute the slash transaction. And this way that connector gets burned, and that means the operator cannot touch the funds. Does that make sense? And since we have multiple operators and we assume one of the operators is honest, so eventually one of the operators will be able to execute a valid peg-out. And all the other ones will get slashed with this kind of setup. For each operator, you have this entire setup. Oh yeah, actually the peg-in transaction is always the same, but you have a peg-out transaction and a kick-off transaction, a slash transaction, this for each operator. So this is the rough idea behind how BitVM bridges work, but I have not explained at all how that black box works. And in BitVM 2, it was quite complicated, and in BitVM 3, this entire black box is essentially replaced by garbled circuits. Yes, please.
How can we be sure that 2 weeks time lock puzzle is available here?
Oh, this is an opcode in Bitcoin that essentially says 2 weeks after you have created this output, you can spend this output, but you cannot spend it before.
I mean, how?
It's an opcode that is just part of the blockchain logic. Yeah. There is some basic smart contracting capability in Bitcoin. It's not just signatures. You also have multi-signatures, but also time locks and hash locks. This is essentially what you can do. But this is a time lock. Yeah. Yes, please.
Just a quick question as well. What's being challenged in the bottom here with the watchtower versus operator?
Yeah, good question. I kind of glossed over that, but it's essentially when they post that kickoff transaction, they essentially say, I witnessed a valid pagout in the site system. So essentially somebody burned their coins in the site system to a particular address. And that means I'm entitled to take money out of the bridge now. And that statement will be proven in a snark, and you can verify it in BitVM. Any other questions? Yes, please. No. This is actually execute like, well, actually, Alice provides this output. Then you pre-sign all of the things that you have to pre-sign here. Then you execute the peg-in transaction. Everything else is off-chain, stored off-chain until actually kick off and the output, the withdrawal happens. Okay, cool. So this is roughly the mechanism. In practice, it's actually more complicated, but this is the rough overview. And now, how can we optimize it with garbled circuits? Or in general, we are optimizing with garbled circuits, and I'm going to explain why this is pretty cool for BitVM. First of all, it was introduced by Jeremy Rubin in April 25. And that was quite funny. Like he garbled circuit built me at MIT Bitcoin Expo, just like I think 2 weeks after we have completed the BitVM 2 implementation. And he talked to me like for 3 sentences or something, and I immediately realized, okay, BitVM 2 is completely obsolete. This is like vastly better. And it was quite a funny moment. And I garbled circuit the entire BitVM alliance, and it turned out Liam Egan, maybe you've heard of him, he's a great cryptographer. He had been working on garbled circuits actually, and he already came up with quite some cool schemes that he hadn't published yet. And then another company called Fairgate, they had also been working on garbled circuits, and like the entire research around garbled circuits exploded in a very quick time. And now many different directions are getting explored in parallel, and like everyone is garbled circuit pilled. And every day, people come up with new ideas and new optimizations to make it more practical. And the fun fact is, it was already possible in 2017, but nobody noticed until 2025. And we had to take that detour to build that monster BitVM 2 to then come to garbled circuits, which are conceptually way simpler and way superior in many ways. Now, like how to upgrade from BitVM 2, or like what's the difference between BitVM 2 and BitVM 3? Well, in general, these BitVMs, they consist of 2 parts. First of all, that snark verifier, which was that black box that I showed you in the graph, and the bridge contract, which is essentially that graph that I showed to you. And the garbled circuits, they make that snark verifier way more efficient. That black box becomes orders of magnitude more efficient. However, the rest of the bridge essentially stays the same. It's more or less the same transaction logic. So you can think of garbled circuits essentially for a drop-in replacement for that BitVM 2 snark verifier. And yeah, to give you a rough overview, in BitVM 2, like the main 2 transactions in the graph are the so-called assert transaction. In the assert transaction, the operator publishes a proof. They have to Lamport sign that proof for a particular reason. And that means, sorry, they not just have to Lamport sign the proof, they also have to Lamport sign the execution trace of the verification of that proof. And long story short, that is roughly 2 megabytes of data that they have to publish in the chain. And the disproof transaction is up to 4 megabytes. And in total, that sums up to 6 megabytes in the worst case. You don't have to put that on chain, like as long as everyone is honest. But if somebody is lying, then you have to be able to disprove them. So in the happy path, it's actually just a couple bytes that you have to put on chain. But in the unhappy path, you have to be able to put up to 6 megabytes of data onto the chain. And it's like 1.5 blocks worth of block data, and that is, of course, very expensive. It's on the order of, let's say, $10,000 or something, depending on how high the fees are. And in BitVM 2, it becomes vastly more efficient. Like the assert transaction, even like with an naive encoding, it's just 70 kilobytes, and you can get it down to roughly 10 kilobytes with a couple tricks. And the disproof transaction is extremely small, from 4 megabytes down to 200 bytes. So in total, you have less than 70 kilobytes, and that's actually like it's more than 1,000x improvement, since in practice you get here 10 kilobytes, not 70. So with a quite simple trick, we get 1000x improvement over the state of the art. And that's why everyone is so excited about garbled circuits these days. And what's the key idea? Well, we are using garbled circuits for so-called conditional disclosure of secrets. So we are disclosing a secret on a particular condition. If a particular condition is met, then you learn a secret. That's actually very different from how they have been historically used. Usually they are used for like multi-party computation, but we are using actually a different property of garbled circuits. And to give you a high-level idea of how that looks like, well, we have some kind of black box. This is our garbled circuit, and we kind of agree on that black box. And then that operator, they publish a snark proof, and you can feed that snark proof into the black box and essentially verify that snark proof in that black box. And if that snark proof is incorrect, if it's faulty, then you learn a secret. So that's, on a high level, the idea. You get a snark proof by the operator. They have to publish in the chain. You can essentially force them to publish the snark proof in the chain. Then you put it into that black box garbled circuit thing. And if the snark proof was incorrect, then you learn the secret. And knowledge of that secret is a fraud proof. That's the key idea behind it. If you know that secret, that means the operator lied. They provided an invalid proof. And you can prove to the chain that you know that secret because it's just revelation of a hash pre-image essentially. And this way you can easily prove to the chain that the operator lied. Yeah, that's what I just said. How does it work? Garbled circuits, they are essentially garbled gates. How do we garble a gate? Here, I guess everyone is familiar with truth tables. Here, for example, we have AND. Of course, we can represent any kind of function, any kind of computable function as essentially as a logic gate, as a logic circuit, and we can represent it with gates like AND, OR, XOR, stuff like that. And each of these gates can be represented in such a truth table. And this is like something that you have probably seen 1,000 times before. How do we garble such a truth table now? Well, first of all, we replace these values with so-called labels. These labels, for now, they are just random data. It's just a random 20-byte string, for example. So instead of 0, I write a random 20-byte string here. And first of all, they are secret. And the idea is, like that one party, the operator, they reveal an input. An input would be some assertion to A and to B. So they say, for example, A equals 0, so they reveal A0. And they say B should be 1, so they reveal B1. And then you can look into this table, and you know A0 and B1. And from A0 and B1, you should learn C0. The secret C0. Does that make sense, roughly? If we have this mechanism, then we can garble a gate. And how do we do that? Well, we have a basic encryption scheme. I guess that's very simple for you guys, since you are all cryptographers. We just have an encryption scheme that takes a key and a message and produces a ciphertext. And the decryption function just takes the same key and the ciphertext, and you can retrieve the message from that. And the garbled table now becomes essentially 4 different ciphertexts. The first ciphertext is the encryption of C0 under the key A0, B0. The second ciphertext is again C0 encrypted under A0, B1, and so on. And that essentially means if you learn an assertion to the inputs, then you can decrypt the corresponding output. Does that make sense? Okay, cool. I glossed over here that you actually need verifiable encryption. Because if I just give you 4 random ciphertexts, you don't know anything about these ciphertexts. So I have to prove to you in zero knowledge that they actually decrypt to those C values that I'm claiming that they encrypt to. And once we have that, we have garbled gates. And garbled gates, they are composable. Because as you see here, the input is just these kind of labels, and the output is a label. So you can take the output and put them as an input to the next label. And this is how you compose these gates. And yeah, then you have a garbled circuit, and that garbled circuit has like input labels, and then there's that huge construction of like gates, and then there's an output label. I think I have to speed up a lot. Yeah, and we don't just have any kind of circuit, we have a snark verifier circuit because that allows us to do universal computation. Also, it allows us to compress the state into a very compact thing because the snark is just like 128 bytes or something. And yeah, the snark verification function is just verify, and you put a proof in there, and then it returns true or false. And the protocol is such: the bridge operator publishes a snark proof, which are the inputs to the circuit, and then the challenger verifies that snark, and if they learn the output label for false, that means the proof was incorrect. That is a fraud proof. The operator provided an incorrect proof. Yeah, the challenges and trade-off. A snark verifier is incredibly huge. It's 10 billion gates. And this leads to a huge off-chain cost, of course. The circuit size can be quite large. In the most naive way, it's terabytes. We got it down to gigabytes. Now Liam Egan came up with a scheme that brought it down to, I think, a few hundred bytes or something. And it comes with all kinds of trade-offs. Like you can reduce the circuit size, but then the garbling performance goes down. And you can also make trade-offs with on-chain costs. You can have bigger assert transactions and like slightly bigger disprove transactions, and that reduces the other two. And that's kind of like the trade-off space. And also you can have different security assumptions. So you can have more aggressive crypto assumptions that allows you to do more kinds of magic. And you can use trusted computing to compute the garbling tables faster. Gives you, of course, a huge advantage, but then you need to outsource it to the cloud or something, and you have to trust them with your secret data. And yeah, rough overview about the solutions. Classical YAO style and cut and choose. Then Delbrag is that scheme that Jeremy Rubin came up with. BitVM 3S is something that I came up with. Then BitGC is a classical scheme. It has very small tables, like the circuit is very small, but it's very expensive to garble it. Attribute-based encryption was another idea that people explored. It would result in very small tables, but it's also very expensive to compute. And then there's that scheme by Liam Egan. It's called Glock on Friday at BTC++. You can watch his talk. Very exciting. I totally recommend it. And there is that paper, BitVM with succinct on-chain cost by Viking Cheng, where he summarizes essentially all the ideas that people have thought about. How much time do I have? Technically finished. Okay, I'm going to skip over all these other things here. Yeah, we do have some implementations. You can see them at bitvm.org or like github.com/bitvm. And yeah. Summary, BitVM is almost production ready, launches soon, but it's kind of obsolete now. BitVM 3 and garbled circuits, they are definitely the future. They give you 100x improvement over the state of the art. The challenges are how to tame the off-chain cost, how to tame the garblings, like the garbling time and the circuit size. And many different directions are getting explored right now. It's a very exciting time in Bitcoin research. And yeah, if you're interested in crypto research for Bitcoin, please join us. That's it. Thanks.
Thank you very much. Do we have any questions? One question, maybe? I'm going to give you...
So I have, because of the time constraint, you skip, a bit fast, but I have, captured some bits. So when you do the garbling, I have seen the free XOR and this sort of things. So you are using YAO's garbled circles?
That's just like the simplest idea. I think there's a huge spectrum of ideas. The most simple thing that people are exploring is just YAO style and cut and choose. And the most sophisticated thing is Liam's Glock scheme, which is based on essentially using a designated verifier snark over a binary field, because over binary fields, addition is essentially just XOR, and then like of these 10 billion gates, essentially all of them, except for 10 million or something, are XOR. And yeah, that makes it very efficient for garbling.
Actually, yeah, the cut and choose is to have the malicious, you know, from semi-honest to malicious. Actually, this is, you know, you can build cut and choose, you know, in any scheme, and you can use underlying, you know. So, so my question is actually, are you trying to create a kind of circuit that solves the MPC problem, or you are using MPC to solve the ZK snark?
Well, this is privacy-free garbling, so it's very different than what people are using in MPCs. Like we don't care about actually hiding the function or hiding the inputs, really, because they're public. We don't use any kind of like oblivious transfer or something.
Inputs are also public, or?
Yes, it's just the snark that is
so
published in the chain.
Okay.
And the literature is called privacy-free garbling.
Okay, so you are trying to have a kind of, not the privacy, you don't want to achieve the privacy, but you want to achieve the succinctness. Is that the...
Yeah, the conditional disclosure of secrets is actually the thing that we care about. We don't care about the privacy properties at all. We just care about that you can evaluate that snark in that garbled circuit, and if it's false, then you learn that false label. And only on that condition that the snark was incorrect, you learn that false label. And then this false label acts as the fraud proof.
Okay, yeah. It's interesting. I need to read a little bit more. Yeah. Thank you so much.
Thanks.